Hey folks, hi! Welcome to day 7 of Advent of Code 2024, as it might be very evident from my heptagon face cam today. And if you're new here, I am Jatin Kumar Malik, an engineer who absolutely loves solving these problems every year. Last year, I did a Medium blog post series, and this year, I'm doing YouTube. So, in case you are new here, check out here for day 1 to day 6 discussions. These are spoiler free discussions aimed to help you understand the process behind problem solving and guide you towards finding the solution yourself. So don't worry, I'm not going to spoil anything for you, but let's get started. So it's 11:38 right now in Chicago. The problem has been out for some 30 minutes and I'm just getting to it. So opening that for day 7, our problem is called bridge repair. So let's read it. The historians take you to a familiar rope bridge over a river in the middle of a jungle. The chief isn't on this side of the bridge, though maybe he's on the other side. So, if you have been following this series, we are still looking for the chief historian who is missing from day 1. I hope we find him soon. So, when you go to cross the bridge, you notice a group of engineers trying to repair it. Apparently, it breaks pretty frequently. You won't be able to cross it until it's fixed. And this bridge is a reference to a puzzle from 2022. And you ask how long it will take, and the engineers tell you that it only needs final calibrations, but some young elephants were playing nearby and stole all the operators from their calibration equations. Well, that happened. And they could finish the calibrations if only someone could determine which test values could possibly be produced by placing any combination of operators into their calibration equations, and which is basically our puzzle input. So we are given a test case here. So let me copy this before we read forward so that we can try to do some dry runs and see what we are dealing with. So here each line represents a single equation. So we are given a bunch of equations and it seems like their operators are missing, but let's read. The test value appears before the colon on each line. So this is our test value. It is your job to determine whether the remaining numbers can be combined with the operators to produce a test value or not. Okay. And operators are always evaluated left to right and not according to the precedence rules. So this is interesting. So we are not following, if you know, BODMASS, basically division, multiplication, addition, subtraction before brackets and all. So we will always evaluate this from left to right. And furthermore, the numbers in equations cannot be rearranged. So that's also interesting. So the numbers that are given here, they are fixed. And that helps us in a way. It is trying to reduce the scope of the problem. Glancing into the jungle, you can see elephants holding two different types of operators. So we have a add operator and we have a multiply operator. So now only 3 of the above equations can be made true by inserting operators. So basically, the problem is fairly interesting. So we have given operators, and all these pink lines that you see are the places where some of our operators are missing. And on the left side, what you can see is the test value or the total value that we need for our equation. And the idea is that we want to find out what are the equations that can be made true by inserting either a plus or a multiply operator. And how we will do that is also very interesting. So if you see the first example, it's very intuitive to see that we need a multiplication operator and then this equation becomes correct. And I think that's what it mentions in the first example. The second one is very interesting because it says that it has 2 positions for operators and of the 4 possible configurations. So first of all, first let's see the problem and then we'll come to like some of the thoughts I'm having. But we can see that there are 4 possible combinations. So because there are 2 spaces here, so it is following a pattern of 2:n. So it will, like, for the 1 we have 2 choices, for the 2 we have 4, for 3 we have 8, and so on. And that's probably a hint before I should have given you a hint, but let's see this. So in 3 to 6, 7, there are 2 possible ways of doing this. So we can either have one where we do 81 plus 40 multiply by 27. And this is only possible because remember, we are always doing this and we are not following the mathematical rules. And the second one is 81 into 40 plus 27. And if we were to verify that, I can check that 81 plus 40, since we are going left to right, is 121, and 121 into 27 is indeed 3267. And coming on to the third equation, since we only have one gap, we can only use plus or multiply. So 17 plus 5 is not 83, and 17 into 5 is also not 83. Similarly, we have 156. Still doesn't work. 15 into 6 is 90, and 15 plus 6 is 21, so it doesn't work, and so on. So we have cases, and then we have one more example where we are given 292, and it can be solved in exactly one way, where we say 11 plus 6 multiply by 16 plus 20, and that equals to 292. So that is pretty clear. I think this is the only interesting caveat that we need to follow. So now, how do we get the answer for the puzzle? Let's read forward. So the engineers just need the total calibration result, which is the sum of the test values from just the equations that could possibly be true. In the above example, the sum of the test values for the three equations listed above is 3749. So I see. So for the equations that can be made true, what we are doing is we are taking the test values, and the answer of the puzzle is basically doing a sum of these three values. In this case, it comes together to be 3749, which is our answer. So now what we need to do is we need to determine which equations could possibly be true and what is their total calibration result. And if we take a look at our puzzle input, that's pretty big. So probably now is a good time for you to pause and think how you will approach it. And then I will share like what is my thinking process here. So it's a good time to pause now. So I'm back. So here is how I am thinking about it. So overall, we basically have two problems here. A, how will you try like these operators, so plus and multiplication for all the spaces, and B, how will you verify the test result that is given here. And again, if you didn't think about this, pause the video here, think about that, and I'm here when you get back, and then let's start to do some iteration on top of that. So, all right, are you ready for a couple of more hints? Don't worry, I will try not to spoil the solution for you. But see, in this case, what comes to my mind initially is recursive or an iterative approach, where I can just brute force my way into trying all the solutions. But now remember, we just saw the puzzle input and there are calculations that can be pretty big. And let me walk you through a very quick dry run example of how like something like maybe this example that we did not see, how many test cases it can unfold. So yeah, let's do a dry run of this example here. And as we discussed that since there are three possible choices based on 2 raised to the power n, we have 8 possible configurations. But let's see how that unfolds in real space and time. So we will start with 9. And when we introduce 7, we basically have two options. It can either be 9 plus 7 or it can be 9 multiplied by 7. And then when we introduce 18, it basically unfolds into two more choices where it can be 9 plus 7 plus 18, or it can be 9 plus 7 multiplied by 18. And this also has two options for us where it becomes 9 multiplied by 7 plus 18 or 9 multiplied by 7 multiplied by 18. And then comes the last element, which is 13, which basically makes us expand this a little bit more. So if I have to get some space here and I will zoom out and show it to you, this one becomes 9 plus 7 plus 18 plus, what was the last number? 13. This becomes 9 plus 7 plus 18 multiplied by 13. We are running out of space, so I'm going to take this, maybe write like this and this. So this becomes 9 plus 7 multiplied by 18 plus 13. And this becomes 9 plus 7 multiplied by 18 multiplied by 13. Let's go up it here. Let's write for these two as well. So 9 multiplied by 7 plus 18 and plus 13. And the second option is we take this 9 multiplied by 7 plus 18 multiplied by 13. And we have the last one, which is 9 multiplied by 7 multiplied by 18 plus 13. And the last one, 9 multiplied by 7 multiplied by 18 multiplied by 13. So now that we have sample space, we can see we have, as we said here, that we have total 8 types of calculations. If you see the last level, we indeed have 8 different types of arrangements of these operators that we can use. And the interesting aspect here is to see that when you start brute forcing it and you start calculating it, there is a lot of common calculations that you will end up doing regardless. So you can see 9 plus 7, 9 into 7, and then 9 plus 7 plus 18, 9 plus 7 into 18, this level. This is being reused again and again and again everywhere. So can you think of a way, and it's a very popular technique that we can use in order to not do a lot of these calculations? Because if we do like a crude brute force, we are going to waste a lot of our CPU cycles in just calculating the same arithmetic operations again and again. Can you think of something? Well, yes, the answer is memoization. So memoization is a very interesting concept, and it is often used in DP, which a lot of people are scared of, dynamic programming, to memorize a partial calculation, sort of like a cache. So if you know what a cache is, sort of like a cache, in order to optimize the problem and reduce your sample space by a lot. So you can see here, once we do these 4 calculations, the next time when we get an add 13, we only need to do like 8 more calculations rather than doing all the calculations again, right? And yeah, by optimizing in this way, I think we should be able to write a program that should be fairly quick to solve these equations and get us our answer. So I think now is the time where I will quickly go to my VS Code and write some code to get the answer of part 1 so that we can move towards part 2. So I think it's a good opportunity for you as well to pause and maybe write some code. And I will see you in a few minutes. And hey, look at that. We are back and we were able to get our first gold star. And honestly, it was fairly simple. I don't have any additional pointers to give. I think using a recursion approach with the memoization worked really well. And I will put the code below in the comments or description for my GitHub repo. Please check that out. And let me know if you would like to see an iteration solution. I can also write that and push it, or maybe you can take it as a challenge and see like what would be the key difference between recursive and an iterative solution. So maybe give that a try. But let's move on and see what we have in store for us in the part 2. Usually that's where most of the fun starts to happen. So moving on. So this is the part 2. I am going to hide this solution, although it should not matter because Advent of Code uses different sets of input data. So even if you see my answer, that may not be your answer. And we'll make some space. We'll take some new color, maybe. Let's take purple. And we'll say we are now at part 2. So let's read it. The engineers seem concerned. The total calibration result you gave them is nowhere close to being, yeah, this is a huge number. It's nowhere close to being within safety tolerances. Just then you spot your mistake. Some well-hidden elephants are holding a third type of operator, of course. And the concatenation operator. So the concatenation operator is given to us here. So this is concat. And concatenation operator combines the digits from its left and right inputs into a single number. For example, if we are given 12 concatenation with 345, that becomes 12,345, a single number. And concatenation on a tangent, it's very popular when you are doing string operations. We usually use plus operator to do concatenation. This is in programming usually an OR operator, but hey, who am I to argue with the elves and the fantasy world of historians here? So all the operators are still evaluated left to right. So that condition still stands. Now, apart from the three equations that could be made true using the addition and multiplication, the above example has three more equations that can now be made true by inserting operators. So I think it's taking an example from these values that were there, and let's see which one of them they are. So the first one was 156, 15, 6, and this was like empty. So remember, like both multiplication and addition did not work because we were getting answer of 90s and 21. But hey, now if that we put concatenation operator here, it does become 156. So that is correct. And the another one was 7290. And we had an option of 68615. And now we are given a solution that this can also be made correct. So I'll just use a different color. This can also be made correct if we do 6 multiplied by 8, but concatenate this 6 multiplied by 15. Now the interesting question here to know is that it seems like concatenation is not being used. So we are not following the rules of BODMASS or mathematical rules. So I got it. I think this left to right thing is confusing, and maybe this is the edge case where we'll have to take an extra care. So let's see this again. This is not the way to do it. So I'll probably get the same color again. And if you see here, we are given 7290 and we are given 68615. So the answer this question, this is telling us is 6 into 8 concatenate 6 and then multiply by 15. Because we are evaluating from left to right, you have to basically not think about all your elementary mathematics and just listen to the problem. And this is very interesting. A lot of times when you interview for Google, Meta, Microsoft, Uber, even Atlassian, the questions have this hidden complexity which challenged your existing knowledge. And this is usually done to see that how well you will perform when your basic beliefs are challenged. And will you still be able to perform within the boundaries of the problem? And I think this is one of those examples. So if you see here, what it is actually doing is it's 6 into 8, 48. Concatenate 6 and then multiply by 15, which means it is going to be 486 multiplied by 15, which gives us the correct answer 7290. And if I see the other one, I think there is one more, which is 1. So let me take the correct color. If we take the another one, we can see it is 192, and the operands that are given to us are 17, 8, and 14. And initially, there was no single way of arranging them to do anything, but now we can put a concat operator here and plus here, and then this becomes 170 plus 14, which is equal to 192. So I think the question is clear, but I think we will talk about like what complexity does this add. So let's read ahead. So adding up all 6 test values now, the 3 that could be made before using plus and multiplication, plus the new 3 that can now be also made using the concat produces a total new calibration result of 11387. Just using your knowledge of the elephant hiding spots, determine which equations can possibly be true and what is their total calibration result. So now here is the challenge for part 2. Can you figure out how we will find the correct equations using these 3 operators that are given to our disposal? And I think I would recommend you to pause here, maybe grab a paper, pen, your favorite ID, something, and start to think about possibilities. And the interesting thing to note here is that this builds on top of the first solution. So remember, in the first one, we got all the values except the ones that could not happen. Maybe you can just modify that code slightly to just give you all the equations that were rejected, and then you can start to work on them. Or you can rewrite a whole function and do all things together, up to you. If I had to give you a hint here, our equation has slightly modified. For any time we don't get a result, remember initially we were following 2:n. Everything remains the same, but instead now we are going to do a 3 to the power of n, right? And if I had to show you an example, similarly, let's take this example and I'll use a different color. So now what would happen is that, let's say if you're starting with 17, you will have three choices now whenever you are adding a new number. So it can either be 17 concatenation 18. So the second could be 17 plus 8, or it can be 17 multiplied by 8. And then for each of these possibilities, we will have three more possibilities, just like the last one. So if you had to add 14, you can either concatenate 14, you can either plus 14 or you can multiply 14. And similarly here, you can either concatenate 14 plus 14 multiply 14. And similarly here, concatenate 14 plus 14 or multiply 14. So I hope that helps you here, and probably pause here and think. And I think one thing that we can very quickly note here, that in the initial one, if we were not able to find a solution, we were just rejecting that. But here also, there are certain paths that we can very quickly reject, right? Because our total sum, total product sum, whatever, like the total result of the equation should come to this number. So any case where you are doing an operation and that number goes ahead, like goes more than the number. Here, I think it does not, but let's say for an example, instead of 192, we wanted maybe 90. Hypothetical example. And we will have examples like this in the puzzle input. So in that case, you can probably see, like, as soon as you do 17 into 18, it goes over 90. And since there is no negative operator, which is reducing the value, because concatenation also basically multiplies your value with the power of, it just increases the length of the string, which overall increases the number. So you don't really need to see these paths. Get it? And another optimization, similar optimization here, if you see, once you concatenate 178, there is no other operator you can use, either concatenation plus or multiply, that will get you closer to 90. So this is also a path that we can abandon. It would be a different story if we had like a division operator or a minus operator, but we don't have that. So probably in this scenario, this is the only possible path that you will take forward and you will try to find something. And there still might be some equations where there is no right answer, and we are just going to ignore that. And once we are done, we are going to find what are all the equations that we were able to mark true by using the concatenation operator. And then we are going to do a sum of their result value, and that would be our answer. Now is a good time for you to write some code, and I'm also going to do exactly that. So I will see you in a bit. And hey, hello, we are back. I just had some chai and it seems like we have received the right answer. And I did not make any change. I just followed the approach we discussed. But I just wanted to discuss one thing to showcase like how much difference the memoization can make. And in this puzzle, for an example, we had a total of 850 equations. So that were given in our sample input. And I just did a very quick eyeball and I found like the biggest equation I could find was around 15 numbers long, which means we have 14 spaces for different operators. And if you think about this operation, 3 raised to the power 14, that is 4.7 million. So operations. And it's crazy how it scales because it is scaling exponentially. And if you think about like without memoization, if you had to solve this, probably you should write some code and try that out. But if we want to try to calculate the space and time complexity, while we don't have theoretically any space-time complexity because we are doing everything in memory in the recursion stack, the time complexity is very interesting. So assuming that there is an equation that is n, that is we have total n m equations, and we have equation that is on average n characters long. So that gives us n minus 1 because for 15 numbers we can put 14 operators in between, multiply by n operations. So the big O complexity, and the big O complexity becomes basically 3 raised to the power n. And as you can see, like even for just one equation with 15 characters, you have to probably do these many operations. It's crazy. So let's say if you had to crazy. But on the other hand, just by taking a small hit on the space by storing the intermediate states, we can bring this number down drastically, right? So if we use memoization here, so talking about the space complexity, assuming that each equation is n characters long, and if you have k unique characters, so basically our memoization will take care of all the repetitive calculations. And if you have m equations, our number here realistically becomes non-exponential, and it becomes even better when you're solving like larger and larger equations, as we saw here in this case, like when we were talking about memoization, because a lot of operations are just repetitive. And yeah, considering the time complex, sorry, this was time, not space. And considering the space complexity, our space complexity comes to n into k. And this can become fairly big, but CPU cycles are still much, much more expensive than your memory. And we can just throw a lot of memory to make our CPU computation much faster. And I think it's an interesting exercise for you to do. So maybe pause here, take a look at it, but try to calculate the time difference between both the approach. So if you don't use memoization and ones with memoization, and you will see that the difference between, like, I think probably a computer is not going to be able to execute all those 850 equations in few hours, but this you will probably get it in like few seconds. So yeah, folks, that was our day 7. Our sky art is looking more beautiful than ever. And if you enjoyed solving this problem, please check out my other problems in the series and like, share, and subscribe with your other developer friends who may enjoy knowing behind the scenes of how to approach a problem. And I hope this series is helpful and I make it to day 25. It takes a lot of time to record and edit these videos, but I'm having a lot of fun and I'm hoping that I'm able to add some value in explaining the learning process behind it. So yeah, I think I will probably see you in 22 hours, 5 minutes and 10 seconds, as my screen says, for the day 8. Till then, keep your brain juices flowing and adios.